Imagine sitting beside the window on a flight crossing the Atlantic Ocean. The aircraft has been cruising for several hours. Most passengers are watching movies or trying to sleep, and the nearest coastline is hundreds of miles away. Then a violent bang comes from outside the cabin, followed by a sudden vibration that seems to travel through the floor. When you look through the window, one of the engines no longer sounds or looks the way it did a moment earlier. For most passengers, the conclusion feels obvious. A two-engine airplane has just lost half of its power, so it must also have lost half of its ability to remain in the sky. With nothing but open ocean below, it seems as though the aircraft should immediately begin falling. That is not what normally happens. An engine failure is a serious emergency, but commercial airplanes are designed with the assumption that it could occur. The pilots train repeatedly for it, the aircraft has systems built around it, and the airplane must demonstrate that it can remain controllable and continue flying with one engine unavailable. Depending on where and when the failure occurs, the crew may still have enough performance to remain airborne for hours while diverting to a suitable airport. The reason sounds almost too simple. Engines do not hold an airplane in the sky. They provide the forward force that allows the wings to do that job. When a jetliner moves through the atmosphere, air passes around its wings. The shape and angle of those wings cause them to redirect air downward while creating a pressure difference around their surfaces, producing the upward force known as lift. As long as the aircraft maintains sufficient airspeed, the wings continue generating that lift whether both engines are running or only one remains available. Losing an engine, therefore, does not switch gravity back on or remove the aerodynamic forces supporting the airplane. The wings do not know how many engines are operating. They respond to the airflow moving around them. The engines are still essential because they create thrust, which allows the aircraft to overcome drag and maintain speed. When one fails, the airplane loses a major source of that thrust, but it does not lose all of it. The remaining engine on a large passenger jet can still produce an extraordinary amount of power, enough to keep the aircraft moving through the air while the crew stabilizes the situation and begins planning where to land. The aircraft may no longer be capable of everything it could do with both engines. It might be unable to maintain its original cruising altitude, especially if it is heavy and flying high above the ocean. It may have to descend to a lower altitude where the remaining engine can support level flight more efficiently, and it will generally have less climb performance and a smaller margin for certain maneuvers. However, there is an enormous difference between reduced performance and having no ability to fly at all. If an engine fails during cruise, the first sign in the cockpit may not even be the sound passengers hear. Modern aircraft monitor engine speed, temperatures, oil pressure, vibration, fuel flow, and many other measurements continuously. Warning systems can alert the pilots within moments that one side is no longer producing normal thrust or that an abnormal condition requires the engine to be shut down. The crew's first responsibility is not to begin searching for an airport immediately. It is to keep the airplane under control. Aviators often summarize emergency priorities with a simple principle: fly the aircraft first, navigate second, and communicate after the immediate situation is stable. That order matters because losing an engine creates more than a reduction in power. It also creates an imbalance. When both engines are operating normally, one is pushing from the left side of the aircraft and the other is pushing from the right. Those forces are nearly balanced around the airplane's center line, so they work together to move the aircraft forward. If the left engine fails, while the right engine continues producing thrust, the right side is still being pushed forward while the left side is not. The airplane naturally begins yawing or turning toward the failed engine. At lower speeds and high power settings, such as during takeoff, this turning tendency can become especially strong. The solution is located at the tail. The vertical stabilizer and rudder allow the pilots to create an aerodynamic force that opposes the uneven engine thrust. By applying rudder in the correct direction, the crew can prevent the airplane from continuing to yaw and keep its nose aligned with the intended flight path. A small amount of bank toward the operating engine may also be used, depending on the aircraft and its procedures, to reduce drag and improve performance. This does not mean the pilots are physically wrestling a giant aircraft through the sky with brute force. Flight control systems, yaw dampers, autopilot functions, and other forms of automation may assist in maintaining stability, although the exact response depends on the aircraft and the nature of the failure. Pilots still have to recognize the problem, apply the correct controls, verify what has happened, and follow the appropriate checklist. Identifying the failed engine correctly is critical. Shutting down the healthy engine by mistake would turn a manageable one-engine emergency into a far more dangerous loss of all thrust. That is why cockpit procedures are deliberately methodical. Crews use instrument indications, warning messages, physical control responses, and verbal cross-checks before taking irreversible actions. Once the aircraft is stable, the pilots can reduce drag from the failed side where possible, secure the engine, isolate damaged systems, and examine the airplane's remaining capabilities. The exact checklist varies depending on whether the engine shut down cleanly, suffered internal damage, caught fire, lost oil pressure, or developed another problem. A contained engine failure means damaged components remain largely inside the engine casing. An uncontained failure occurs when fragments escape the casing, potentially affecting nearby parts of the aircraft. The second situation can create additional complications, but airplanes are designed with separation, protection, and redundant systems intended to reduce the chance that one engine problem disables everything else as well. This redundancy is one of the central ideas behind commercial aviation. Each engine generally has its own supporting systems, and critical aircraft functions are not supposed to depend on one vulnerable component. Electrical power, hydraulics, instrumentation, and flight controls are arranged so that losing a single source does not automatically make the airplane uncontrollable. The engines themselves can also power more than propulsion. They may drive generators, hydraulic pumps, and pneumatic systems used for pressurization and other aircraft functions. Losing one engine therefore changes the configuration of the entire airplane, but remaining systems, backup sources, and the operating engine can continue supporting essential functions. An auxiliary power unit, usually located near the tail, may provide additional electrical or pneumatic support in some situations. Batteries and emergency generators create further layers of protection. The goal is not to pretend failures never happen. It is to make sure one failure does not spread unchecked across the aircraft. The timing of the engine failure makes an enormous difference. An engine stopping at cruising altitude gives the crew height, time, and options. An engine failing during takeoff creates a much more demanding problem because the aircraft is close to the ground, heavily loaded, and using high power. There may be only seconds to respond correctly. This is exactly why takeoff performance is calculated before every departure. Pilots do not simply advance the throttles and hope both engines keep working. The aircraft's weight, runway length, wind, temperature, elevation, runway condition, surrounding terrain, and obstacle clearance are considered before the airplane begins moving. From those figures, the crew receives important takeoff speeds that help determine what should happen if a serious problem develops during the acceleration. One of those speeds is V1, often described as the takeoff decision speed. Before reaching this point, there may still be enough runway remaining to stop the aircraft if a major failure occurs. At or after that point, attempting to stop may be more dangerous than continuing because the airplane could run beyond the end of the runway before slowing down. This means a passenger jet may suffer an engine failure during the takeoff roll and still continue into the sky intentionally. To someone watching from the cabin, that can seem completely irrational. If an engine has failed, why would the pilots leave the ground instead of stopping immediately? The answer is that the airplane may already be moving too quickly to stop safely on the runway that remains. It has been calculated and certified so that, under the applicable conditions, it can continue the takeoff on the operating engine after a failure near the critical decision point, clear required obstacles, stabilize, and return for landing. That ability is not an optional bonus added after the aircraft is designed. It influences engine power, rudder authority, wing performance, runway calculations, pilot training, and aircraft certification from the beginning. Continuing the takeoff does not mean the aircraft climbs normally. The rate of climb can be much lower, and the pilots have to control the asymmetric thrust while following a planned engine out path that keeps the airplane clear of terrain and obstacles. At airports surrounded by mountains or buildings, those procedures may be carefully designed for the local environment. The crew may initially continue straight ahead, retract the landing gear, manage the flaps according to procedure, climb to a safe altitude, and only then begin running detailed checklists or turning back toward the airport. Rushing into a steep turn while slow, low, and operating on one engine could make the situation worse. This is also why pilots practice engine failures in full-motion simulators until their response becomes disciplined rather than emotional. The simulation can recreate an engine failure at the worst possible point during takeoff, along with bad weather, warning alarms, system problems, and a heavy aircraft. Crews learn to resist the instinct to react too quickly and instead follow the sequence that preserves control. The passengers may hear unusual engine sounds, feel the aircraft yaw, notice a slower climb, or see emergency vehicles waiting near the runway when the plane returns. Inside the cockpit, however, the event is being handled through procedures developed specifically for that moment. Once the aircraft reaches a safe configuration and altitude, the emergency changes from an immediate control problem into a planning problem. The airplane is still flying, but it now has reduced performance, altered systems, and only one source of engine thrust. The next question is no longer whether the aircraft can remain in the sky. It is where the pilots should take it next. Once the aircraft is stable and the failed engine has been secured, the pilots have to decide where to land. The nearest airport is not automatically the safest choice because a runway that looks close on a map may be too short, surrounded by dangerous terrain, covered by bad weather, or unable to support an aircraft of that size. The crew also has to consider emergency services, fuel remaining, the condition of the airplane, and whether the weather is expected to improve or deteriorate. If the failure happens shortly after departure, returning to the same airport may seem obvious, but the aircraft could now be too heavy to land immediately. Passenger jets often take off carrying enough fuel for several hours of flight, and that fuel contributes a huge amount of weight. Landing above the aircraft's recommended limit can place additional stress on the landing gear and structure, so the pilots may need to remain in the air while burning fuel or, on certain aircraft and in specific circumstances, release some of it before approaching the runway. However, landing overweight may still be the correct decision when the situation is urgent. The crew is constantly balancing different risks rather than following one rule in every emergency. A damaged engine, fire warning, or other serious problem may make an immediate landing safer than spending additional time in the air simply to reduce weight. During cruise, the decision can become even more complicated because the aircraft may be hundreds of miles from the airport it departed and hundreds more from its destination. The pilots and airline dispatchers examine every realistic alternative, compare weather and runway conditions, and choose the location offering the safest overall outcome. This process becomes especially important over the ocean, where suitable airports may be separated by enormous distances. The system allowing twin-engine airliners to operate on these routes is commonly associated with ETOPS, a set of standards governing how far certain aircraft can fly from an adequate diversion airport. The name is often jokingly explained as engines turn or passengers swim, but the real system is far more serious. It requires the aircraft, engines, airline, maintenance program, and flight operation to meet strict reliability standards before long routes over remote areas are approved. Decades ago, twin-engine airplanes were generally kept much closer to diversion airports because engine reliability was lower, and regulators were cautious about allowing them deep over oceans or isolated terrain. Long-distance routes were often dominated by aircraft with 3 or 4 engines because the extra engines appeared to provide more security. As jet engines became dramatically more reliable, manufacturers demonstrated that a modern twin-engine aircraft could continue safely for long periods after losing one engine. This allowed routes to extend farther from land, but only after engineers and airlines proved that the aircraft's systems could support the diversion. An ETOPS flight is not simply sent across an empty ocean with a few airports casually marked on a map. Before departure, planners identify suitable alternates along the route and examine their forecasts, runway conditions, operating hours, emergency services, and ability to handle the aircraft. They also calculate how long the airplane would take to reach one of those airports after an engine failure or another serious system problem. The route may be adjusted so the aircraft remains within the approved diversion time. If weather at one alternate becomes unacceptable, another airport may be selected or the flight path may change before departure. Conditions continue to be monitored while the airplane is in the air because an airport that looked suitable 6 hours earlier may no longer be usable when the aircraft reaches that region. The remarkable part is that some modern aircraft are approved for diversions lasting several hours on one engine. That does not mean airlines expect engines to fail regularly. It means they must prove that the aircraft can handle an extremely unlikely failure without turning it into a catastrophe. Engine reliability is one reason this is possible. Modern turbofan engines operate in punishing conditions, with internal components spinning at enormous speeds while temperatures inside certain sections become hot enough to weaken ordinary metals. Despite that, they can run for thousands of hours because almost every part is designed, monitored, inspected, and maintained with extraordinary precision. Sensors continuously measure vibration, temperature, pressure, rotational speed, oil condition, and fuel flow. Airlines can compare this information across flights and detect patterns that may suggest a component is beginning to deteriorate. Maintenance is increasingly based not only on waiting for something to break, but on identifying warning signs early enough to replace or inspect the part first. Engine components are also inspected at scheduled intervals, sometimes using small cameras inserted through access points so technicians can examine internal blades without completely disassembling the engine. If damage, cracking, unusual wear, or foreign objects are discovered, the engine can be repaired before returning to service. Even with all of this protection, failures can still occur. Birds may enter an engine during takeoff or landing. Internal parts may break, fuel contamination can create problems, and volcanic ash can damage several engines at once. The system is designed around the reality that no machine is perfect. One of the most famous aviation incidents involving engine failure happened in January 2009 when U.S. Airways Flight 1549 struck a flock of large birds shortly after departing New York's LaGuardia Airport. Both engines lost usable thrust while the aircraft was still low over one of the most densely populated cities in the world. The crew quickly determined that they did not have enough altitude to reach a nearby runway safely, so Captain Chesley Sullenberger and First Officer Jeffrey Skiles prepared to land on the Hudson River. The aircraft touched down on the water and remained largely intact, allowing all 155 people aboard to survive. That event is remembered as an extraordinary emergency landing, but it also demonstrates another fact about airplanes that many passengers misunderstand. Even with no engine thrust at all, a jetliner does not simply drop vertically from the sky. It glides. A passenger aircraft has a much worse glide ratio than a dedicated glider, but its wings still produce lift as long as it continues moving through the air. Without thrust, the airplane gradually trades altitude for forward distance. The pilots lower the nose enough to maintain a safe airspeed and guide the aircraft toward the best available landing area. Depending on the aircraft and conditions, a jet at cruising altitude may be able to travel a significant distance while descending. The exact performance depends on weight, configuration, wind, damage, and speed, but the important point is that loss of thrust does not mean loss of control. This has happened in several remarkable real-world cases. In 1983, Air Canada Flight 143 lost power in both engines after receiving insufficient fuel because of a calculation error involving different measurement units. The Boeing 767 became known as the Gimli glider after the crew successfully guided it to a former Air Force base and landed without engine power. In 2001, Air Transat Flight 236 suffered a fuel leak over the Atlantic and eventually lost thrust from both engines. The crew glided the Airbus A330 toward the Azores and landed safely after traveling an extraordinary distance without powered engines. These incidents are extremely rare, but they show why pilots train to manage energy rather than thinking only about engines. Altitude, airspeed, wind, and distance become resources. A crew that protects the correct airspeed and understands the aircraft's glide performance can continue making controlled decisions even after propulsion is lost. With one engine still operating, the situation is far more manageable. The remaining engine helps maintain speed, gives the pilots more time, and may allow the airplane to remain level at a lower altitude rather than descending continuously. It also supports electrical and hydraulic systems that make controlling the aircraft easier. The landing itself requires careful planning because the airplane is no longer operating normally. The crew may choose a runway that reduces crosswind, offers more length, and provides emergency vehicles with easy access. They will usually avoid unnecessary complications and prepare for the possibility that the remaining engine or another system could develop a problem. The approach may be flown at a slightly different speed, and the crew has to be cautious about using too much power because asymmetric thrust becomes more noticeable when the operating engine works harder. Once the aircraft touches down, fire crews may inspect the failed engine, and the airplane can be moved away from the runway when it is safe to do so. Passengers sometimes imagine that a successful one-engine landing depends on one pilot performing a heroic maneuver. In reality, it depends on an entire system. The pilots control the aircraft and make the final decisions, but air traffic controllers clear routes and runways, airline dispatchers provide weather and airport information, cabin crew prepare passengers, maintenance teams advise on technical issues, and emergency services wait on the ground. Long before the flight began, engineers designed the airplane around this possibility. Test pilots proved its performance, regulators examined the results, and simulator instructors trained the crew to respond without panic. Certification testing is especially demanding because manufacturers must demonstrate that the aircraft remains controllable after an engine failure during critical phases of flight. Engineers study how the airplane behaves at low speed, during climb, and with one engine producing high thrust while the other produces none. The vertical tail and rudder must be large enough to counter the imbalance. The operating engine must provide enough performance under defined conditions, and the aircraft must meet climb requirements after takeoff. The design is tested at difficult weights, configurations, and weather conditions rather than only under ideal circumstances. Pilots also practice failures that occur at awkward moments, including during takeoff, shortly after rotation, while climbing through clouds, and during approach. The objective is to make the response systematic even when alarms, vibration, noise, and time pressure arrive together. This is one reason aviation procedures can look slower and more deliberate than passengers expect. The safest response is rarely to begin moving switches immediately. Crews confirm the problem, divide responsibilities, follow checklists, and cross-check important actions because a rushed mistake can be more dangerous than the original failure. Modern commercial aviation is built around the idea that individual parts will eventually stop working. Instead of assuming perfection, engineers create layers of protection so one broken component does not bring down the entire aircraft. There are two engines, multiple electrical sources, separate hydraulic systems, backup instruments, emergency power, redundant computers, and crews trained to continue operating when part of the system disappears. Not every airplane uses the same design, but the philosophy remains consistent. An engine failure is serious because it removes performance and reduces the number of remaining options. It may force the flight to divert, create an expensive inspection, strand passengers, and require major repairs. What it normally does not do is instantly make the aircraft incapable of flight. The wings continue generating lift, the remaining engine continues producing thrust, the rudder counters the imbalance, and the pilots follow procedures designed around the exact emergency they are facing. The next time you look out the window and see two engines beneath the wings, remember that the airplane was not designed on the assumption that both would work perfectly forever. It was designed so that if one of them stopped, the rest of the aircraft would still have a plan. That is the real reason a plane can lose an engine and continue flying. It is not because the failure is harmless or because the aircraft has unlimited power. It is because every part of the system, from the size of the tail to the training of the crew, was built around the possibility that one day an engine might go silent. Commercial airplanes are safe not because nothing ever fails. They are safe because when something does, the aircraft is already prepared to keep flying.